The graphs of radical functions can be transformed by using methods similar to those used to transform linear absolute value, quadratic, and polynomial functions. So the general equation, the general form of a square root function is, and it's got a little asterisk next to it, y equals a times the square root of bx minus h plus k. And let's go through what all the different types of transformations are. If this is not in your notes, then add this to your notes next to the equation. So a is your affects you vertically. Right? So it's a vertical stretch if a is greater than 1. It's a vertical shrink if a is between 0 and 1. It's a if it's negative, it's a reflection over the x-axis. Right? So B is affects us horizontally. Right? And it's actually a little counterintuitive. I don't know if you noticed that. So when we were back here doing the stretches and the horizontal stretches and shrinks, back here, one more I think. There we go, that one's good enough. All right, so notice that a smaller value, right, stretched it. Right? For this particular graph, and the square root one as well, right, our horizontal stretch the factor, we stretched by a factor of 1 divided by 1/5. We take the reciprocal, right? So that would be equal to 5, right? So it's 5 times larger horizontally. Likewise, our graph here, right? So our horizontal shrink it's 1/3 is our factor, how we're growing horizontally. So 1/3 the growth horizontally. All right, so it's the reciprocal. And you might wonder why. Well, if you think about it, so if I have a number like 1/5, I'm going to have to use a much larger number to get to the same place. Like I had to plug in 5 just to get to 1. On the other hand, if I have a number greater than 1, it took a smaller number, like 1/3, to get to 1. Right? So that's how those coefficients in front of x impact our growth horizontally. Let's go back to the general equation. Right? And then, so we have a horizontal stretch if b is between 0 and 1. We have a horizontal shrink if b is greater than 1. And then if it's negative, we reflect across the y-axis. And then h and k translate our graph horizontally and vertically. H is a horizontal translation. Right? So the signs are the opposite. Positive means left, negative is right, because there's already a negative there. Right? So if you think about it, I'm going to have to put in a larger value, right, to get to the same value if I'm subtracting. Right? So that's why it moves to the right. I'm going to have to put in a smaller value, right, if I'm putting in something negative to get to the same place. So it moves it to the left. Right? So the negative's already there, that minus h. Right? So a negative number is going to change it to a positive. That means left. A positive number is going to just stay negative. That would move it right. And then vertical translation, up and down. If you add something positive, it moves up. Add something negative, it moves down. Right? You do need to know how all the different values affect your graph. And we are going to be using not tables of values to graph these, but the rules for translations, and actually the rules for transformations. Right? Our translations, our dilations, our rotations, or excuse me, reflections, no rotations. All right, so transformations of square root and cube root are shown below. So it's the same for square root and cube root, right? So whether there's nothing there and it's a square root, or the index 3 and it's a cube root, exact same rules, right? So A is our vertical stretch or compression, right? And the factor is whatever A is. It's the reciprocal for B, right? So if we're stretching horizontally, we're going to have 1 over B. If we're shrinking, compressing horizontally, we're going to have, so we're going to plug in a B there, it's going to flip, and it's just going to be B. It's not going to be, it's going to be, it's not going to be 1 over anymore, right? Because if I'm shrinking by 1/3, right, and I have 1 divided by 1/3, and I simplify that, that's the same as 1 times the reciprocal, which was 3, right? And that's the graph that we did with the stretch. All right, so right, and so we just multiply by B. You can either multiply, or I'll show you how you can do it using transformations. Right, either is okay with me. And then H is a horizontal translation. If it's x minus H, it's to the right. X plus H is to the left. K is positive, it's up. K is negative, it's down. And I know you have one of these in your notes, one of the general equations. I think it was the other one, the one with all the rules summarized. All right, so multiple transformations can be applied to any radical function. To graph using transformations, you're going to graph your base graph first. All right, I'm looking for the base graph. I don't see a base graph, you lose points, right? Because we're using transformations, right? The other way we would graph is with the table of values, right? So it's not like we have a whole lot of points to work with. It's not like we have x-axis, we necessarily have x-intercepts, y-intercepts, and turning points. We don't have any turning points, right? We don't have two or three x-intercepts, right? We're going to be relying on that base graph and the transformations. All right, so we're going to graph our base graph. If there is a stretch, a vertical or horizontal stretch or compression, you need to take care of that first. All right, so change x values first for stretches and compressions applied to x. Then take care of your dilations, reflections, if your vertical dilations and reflections. All right, so these are the coefficients in front of y. Or, I mean, in front of the radical, excuse me. So coefficients in front of y. Right, so horizontal, then vertical, right, and reflection, and that includes reflections, and then translate, right, from step 2, or base graph for graphs without any dilations or reflections, right? All right, so let's take a look how this looks. All right, so we're going to graph our function and identify its domain and range. We're going to graph the parent function first, and then we're going to transform it. All right, so our parent function is the cube root function, right? F of x equals the cube root of x. So we have 0, 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 2. You'll have these memorized if you don't already. -1, -1, and 1, 2, 3, 4, 5, 6, 7, 8, 2, or -8, 2. All right, so there's our cube root parent graph. All right, so let's see how we're going to transform it. We have a coefficient in front. We need to dilate that dilate our graph by a factor of 2. So we're going to multiply the y values by 2. Right? So notice that we don't have to do we don't have to like create a table of values. We're just going to make our y values twice as much. If you multiply 0 by 2, it's still 0. If you multiply 1 by 2, it's 2. If you multiply 2 by 2, that's 4. If you multiply -1 by 2, that's -2. And you multiply -2 by 2, you get -4. Right? So the first thing we do is we graph the dilation. You have to do the dilation before the translation. Right? Otherwise, it won't be the same graph. Right, so the blue graph is y equals 2 times the cube root of x. Right, so here we're going to have 3 graphs. We're going to have our original parent function, y equals the cube root of x. We just multiplied the y values by 2. That gave us y equals 2 times the cube root of x. And now we're just moving the graph. Right, so we have x minus 2. We're going to translate it 2 units to the right. Right, it's under the radical, so it moves right and left. It's negative, it's going to move right. So I'm just going to take those points, those key points on the blue graph, the dilated graph, and just move them to the right. So here's 2 to the right, 1, 2 to the right, 2 to the right, 2 to the right, and 2 to the right. I think I moved everybody. And there we go. Right? And so the red graph is the graph that we want to graph. F of x equals 2 times the cube root of x minus 2. There's the graph with all of the with the dilation and the translation. No matter what is done to your cube root function, its domain and range is all real numbers. And we're done with this one. Okay? So these graphs go by pretty quickly. What happened to the rest of my range? There we go. Right? And there we're done. Let's do another one. Right? Oh, by the way, follow along in your notes. I didn't mark on mine which ones are in your notes. You just follow along, and every time you see one that are in your notes, then you write that one down. All right? And you can pause the tape. All right? So you can look down, see is in your notes. Oh, that's in my notes. All right? So then you can watch it, and then pause when I get to the end, and you can write down what I write. Right? You don't have to do it the exact second I do it. You can wait till I finish, and then write down the notes. All right, so now let's take a look at this one. Something happened to the radical here. So we're using the graph of f of x equals the square root of x as a guide. Right? That's our parent function. We're going to graph our parent function first. You'll be able to figure out your parent function by looking at the radical. Is that a square root or a cube root? Do you see an index or not? If you don't see an index, it's a square root. Our base graph for the square root is 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3, and that's all that will fit on this particular graph. Right? And we want these nice friendly points. And I stayed away from anything that's not a perfect square. All right, we have a negative in front of the radical. We need to take care of that first. The negative in front will reflect our graph across the x-axis. So now let's graph that one. All we need to do is now make the same points, but on the negative side. Right? We're just flipping the graph over. Remember when you were in geometry and you did reflections? That's all we're doing, reflecting across the x-axis. Right? So the black graph, of course, is y equals the square root of x. The red graph is y equals negative square root of x. But we want negative square root of x minus 4, which means we're shifting it to the right. Graph is moving to the right. So translate it 4 units to the right. So you just take those nice big red points there and move them all 4 to the right. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Did I move? Oh, I forgot this one. 1, 2, 3, 4. Almost forgot that one. All right, so now let's graph. And this is the graph of our function. This is g of x equals negative square root of x minus 4. So on a function, a radical equation, where there is a dilation or reflection and a translation, you should have 3 graphs. Parent, the dilation or reflection, and then the translation. All right, and our domain and range are not all real numbers this time. All right, square root's got a restricted domain and range. Notice the smallest value on our graph is at 4, right? Because we can't have any negative numbers and get a real number. So 4 is the smallest thing I can plug in, and we can actually plug it in, right? It's not approaching 4, it's reaching 4. So, whoops, what the heck happened there? So put in the bracket as soon as I try to erase this. There we go. So it should be a bracket and then 4. It's going to keep on growing forever and ever, and then parentheses. The range were reflected, right? So the square root's going to be positive, but if you multiply it by -1, you're going to get nothing but negative numbers, right? So this is going to head to negative infinity, and the largest number we can plug in, or excuse me, the largest number that we can have would be 0, right? Our square root here cannot be positive, right, because we're multiplying by negative numbers. But we can hit 0. Right? If we plug in 4, right, the square root, negative square root of 4 minus 4, negative 0 has no meaning. It's still 0. Right? There's no such thing as a positive 0 and a negative 0. It's just 0. Right? Second one done. Let's graph another one. And any moment now should come up. Oh, here it is. I'm just waiting. It came up. All right, so now we're going to graph f of g of x equals the square root of negative x plus 3. We need to first graph our parent function, which is the square root of x. All right, so square root of x, of course, we just did it. 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. If we had more space, we'd also graph 16, 4, but we don't. So we won't. I overshot just a teeny bit. Well, you can see where my points were really aiming. That looks a little bit better. All right, so we have a negative inside the radical. Right? That's not going to reflect it over the y-axis. It's going to reflect, it's not going to reflect it across the x-axis. It's going to reflect it across the y-axis. And how come? Normally, we can only plug in positive numbers. So if that were the square root of x, I could just plug in positive numbers, right? That's the only numbers that are going to give me real numbers, the only x values, right? So if I plug in a negative into this, I'm going to get imaginary numbers, right? But if I plug a negative into this, that's good, because I'm going to get real numbers, right? So I'm going to get rid of this, and let's graph our first transformation, which is the reflection. All right, so now all of our x values are negative. All right, so you're just going to reflect it over the y-axis. All right, just like when you were in geometry, right? Just reflecting, you're just counting the distance, right? So if I'm 1 to the right, I'm now 1 to the left. If I'm 4 to the right, I'm now 4 to the left. And if I'm 9 to the right, actually fit this in actually. I'm now 9 to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I can leave that there. The graph makes it right over it. All right, and now we need to, of course this has got a little glitch there. Now we need to translate it. All right, the 3 is not under the radical. It's outside the radical. All right, so that means up and down. And in this case, since it's positive, we're going to translate 3 units up. All right, so our whole graph is just going to move up 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. That number's a little high there. 1, 2, 3, and that's it. All right, so now here's our graph. So if you can add and count and multiply and reflect, you can graph square and cube roots. Right? It's really not that hard, right? I just take that base graph. I just had to graph 4 points, right? And then we reflected it, and then we translated it. Right? Our domain. Now I have no positive numbers. There's nothing for the right graph on the positive side. Nothing but negatives, right? Because I need to plug a negative in there to get something positive. And we can plug in 0, right? That would just give us the square root of 0. The range, right? Notice our smallest y value is right there, right? That's the smallest y value. The whole graph has been shifted up 3. Right? If I take a square root, I'm going to get positive numbers. But if I shift it up 3, I can't get anything less than 3. But it's going to keep on growing vertically. Right? It's going to keep on growing in the y direction. Right? Oh, was that 3 down? Let's graph another one. All right, so here we're graphing the cube root of x plus 2 plus 3. The plus 3 is not under the radical, so that's going to be a vertical transformation. I did put a table of values there. You don't need a table of values for me. I think you could remember 5 points, but you certainly can write it down if you like. 2, 3, 4, 5, 6, 7, 8, 2, and then -1, -1, and then we need our last point. So 2, 3, 4, 5, 6, 7, 8, there we go. Right, and then here is our parent function, that one is y equals the cube root of x. The last several, we needed two graphs, right? One for the dilation, reflection, and then one for the translation. Not this one. It's got only a translation, so we can just graph one more time. The +2 under the radical here, right? It's moving it horizontally. It's a plus. It's 2 units left. Adding 3 to the whole function is going to move that 3 units. Well, I should probably change the ordering of how I wrote them because it doesn't make a very good sentence. So let's do the 3 units up first. 3 units up and 2 units to the left, because to the up sounds really strange. All right, so now if you can count 3s and 2s, you can do this. All right, so 3 units up and 2 to the left. I'm going to actually count left and then up. All right, so my last point is over here. 2 to the left, 1, 2, up 3, 1, 2, 3. All right, there's that point right there. And then over here, 1, 2, 1, 2, 3. By the way, the next one is going to be here and here because they make that line. All right, and we can actually check that out. So here we are, 1, 2, 1, 2, 3. You see it lands in the right spot. 1, 2, 1, 2, 3. Our last point, 1, 2, 1, 2, 3. All right, so there are our points. And here's our graph. That long, skinny S. All right, so the black graph, of course, was y equals the cube root of x. The green graph, we've been shifted, is g of x equals the cube root of x plus 2 and then plus 3. By the way, sometimes people write it like this. It's the same thing. So if you see this, 3 plus the cube root of x plus 2, don't be confused. It's the same graph. Do you know why people might switch it? Well, it's something you sometimes do when you're looking at these radical functions. You think that 3 is also under the radical. You forget that the radical ended, or you didn't realize the radical ended. So by putting the 3 in the front, you can easily tell it's not part of the radical. That's why a lot of times the horizontal might be moved to the front. Right? Either way, it's the same equation. Right? That order we don't put those numbers. The order we add in does not matter. Right? So notice our graph has just been shifted a little bit. Right? It's still going to reach. We can still plug in all real numbers, and it still will reach all real numbers, but the same numbers aren't going to be paired together anymore because our graph's been shifted. But there's our domain and range. Right? Let's move on and graph another one. That was example 4, multiple transformations. I forget how many I have, maybe 6 or 7. Probably closer to 7, maybe 8. All right, so we want to use the graph of the square root of x as a guide to graph our function here. All right, so we have a couple things going on here. All right, let's graph our base graph first. 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3, and graph. There we go. There's y equals the square root of x. All right, so we do have a vertical stretch as well as a reflection. It's in front of the radical, not under the radical. So that means it's vertical. All right, so our parent function is going to be our parent function is f equals the square root of x. Stretched by a factor of 3, and it's reflected across the x-axis. Right, because it's in front. If it was under the radical, it would reflect across the y-axis because it would change our x values. If it's in front, it reflects over the x values because it changes our y values. Right? So if it's under the radical, changes the x values, so it reflects over the y-axis. If it's in front, it changes our y values, so it's going to reflect over the x-axis. All right, so we'll just draw the same thing, but we're going to reflect it and stretch it. Now, you could do the stretch and then the reflection, or you can do it all at one time. Right? So normally if I was stretching, right, instead of 1, I'd do 1, 2, 3, right? I'd make it 3 times as much. Do the same thing. It's going to be 3 times as much, but in the negative direction, right? Because we have by -3. If it helps, you could multiply 1 by -3, and you'd get -3, right? So we're going to stretch it twice, 2 times as much, but in the negative direction. So we're going to have 1, 2, right? Stretch twice as much. All right, so here we're 3 away from the x-axis. Going to stretch it twice as much. All right, so 3, 3 in the negative direction. Right? So 6, 4, and 3. Right? And all it is I just doubled my y value. Or excuse me. Oh, tripled. Well, I tripled one of them. Then I decided to double. Forgot what the scale factor was, I guess. All right, so 1, 2, 1, 2, 1, 2 belongs down here. All right, so 2 times -3 is going to give you -6. 3 times -3 is going to give you -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's look how fast our graph is growing. 3 times as fast. There we go. There's our reflection and our dilation. And now we're just translated 1 unit down. Right, just moving 1 unit down. Right, because it's negative and it's not under the radical. Right, so just count down, count 1 down. Move every point 1 down. And there we go. Then connect the dots. All right, and remember to start it at 0, 1, right? Because it reflected down, it translated down 1. We've got a restricted domain and range here. All right, we are reflected, so that means we're on the negative side. The largest x value, right? Our largest x value. Excuse me, I'm looking at the range. I'm thinking ahead, I guess. We're on the positive side for the x. Then the range is the negative. I'm already going ahead. All right, so on the positive side, our smallest value is 0, right? So if I were to draw a line here where the graph starts, right, it starts at 0. All right, so our domain 0 to infinity. All right, it didn't change. If you shift your graph up and down, the square root function up and down, or you dilate it or reflect it, it's not going to affect your domain. If you reflect it over the x-axis, that is. The range is the one that's been changed the most. Domain wasn't changed at all, but the range has been changed because we're reflected. So we're all negative y's, and the largest was -1. You see that point right there? That's starting point. That's our key point, our starting point. All right, so our range was -infinity to -1. I don't like this to go too long. So when I hit the 30-minute mark, I usually like to stop. I've got 1. How many more to graph? 2. And 3. Enough for me to say that'll go on the next podcast. Thanks for watching. Bye for now. So in the next podcast, we'll look at some more translations. Bye for now.